Have you ever wondered what it would feel like to discover we're not alone in the universe? Well, that moment might be closer than you think. Deep in the constellation Leo, astronomers have just detected something that could change everything we thought we knew about life beyond Earth. We're talking about a world so promising that scientists are 99.7% certain they've found actual living organisms thriving on its surface. This isn't just another maybe. This isn't another could be. This is the closest thing to confirmed extraterrestrial life that humanity has ever discovered. And by the end of this video, you'll understand exactly why this discovery is sending shockwaves through the scientific community and why it might be the most important finding in human history. But first, let me paint you a picture of what we're dealing with here. Imagine a planet 8.5 times more massive than Earth, wrapped in a thick hydrogen atmosphere, orbiting a red dwarf star 120 light-years away. The temperature on this world hovers at exactly 120 degrees Fahrenheit. That's hot tub temperature spread across an entire planet. And in that alien atmosphere, the James Webb Space Telescope has detected something extraordinary. The planet, designated K218b, contains a molecule called dimethyl sulfide. Now, that might sound like scientific jargon, but here's the thing that'll blow your mind. On Earth, dimethyl sulfide is produced exclusively by living organisms. Marine bacteria create it. Certain algae pump it out. Some plants release it as part of their normal biological processes. But no geological process, no chemical reaction, no non-living system has ever been observed creating this molecule. So when we detect dimethyl sulfide in the atmosphere of a planet 120 light-years away, we're essentially looking at a neon sign that says, life lives here. The statistical confidence level is staggering, 99.7%. To put that in perspective, imagine flipping a coin 1,000 times and getting heads 997 times. The probability of that happening by pure chance is so small, it would never occur in the entire history of the universe. This level of certainty is unprecedented in exoplanet science. Most discoveries of atmospheric molecules on distant worlds barely reach the threshold for publication in scientific journals. But K218b represents a quantum leap in our ability to detect life beyond Earth. When scientists say they're 99.7% certain that life exists on this world, they're making a statement as reliable as any fact in science. The James Webb Space Telescope didn't just stumble upon this discovery. It required operating at the absolute limits of technological capability. The dimethyl sulfide signal is extraordinarily faint, just a few parts per billion in the infrared spectrum. To detect it, Webb had to measure wavelengths of light to an accuracy that's like measuring the width of a human hair to the precision of a single atom. But here's where things get really interesting. K218b isn't just alive. It's potentially more habitable than Earth itself. This world belongs to a class of planets called super-Earths, worlds larger than our own but smaller than Neptune. Until recently, astronomers dismissed these planets as inhospitable gas balls, too massive to support life as we know it. K218b forced scientists to completely reimagine what a habitable world could look like. The planet's massive size creates surface gravity nearly 3 times stronger than Earth's. You might think that would be a disadvantage, but it's actually a blessing in disguise. That intense gravity holds the atmosphere in place with an iron grip, preventing it from bleeding away into space, like Mars lost its atmosphere billions of years ago. Even the most violent stellar flares from the host star cannot strip away this world's thick atmospheric envelope. The atmosphere itself defies everything we thought we knew about habitable worlds. Instead of the oxygen and nitrogen we breathe, K218b's atmosphere is dominated by hydrogen and helium. On Earth, hydrogen makes up less than 1 part per million of our atmosphere. On K218b, hydrogen comprises the vast majority of the atmospheric envelope. creating a completely alien environment. This hydrogen atmosphere creates what scientists call a reverse runaway greenhouse effect. Instead of cooking the planet like Venus, the hydrogen acts as a perfect insulator, maintaining stable temperatures across the planet's surface. The thick atmosphere redistributes heat so efficiently that even the night side of the planet, which never sees sunlight, remains warm enough for liquid water. But the really mind-blowing part is what this means for life itself. The chemical signatures detected by Webb paint a picture of a world where life has not only emerged, but thrived. Alongside the life-indicating dimethyl sulfide, the atmosphere contains methane, carbon dioxide, and water vapor. This cocktail of molecules suggests active biological processes operating on a scale that dwarfs anything we see on Earth. Think about it. If life on K218b is producing dimethyl sulfide at levels detectable from 120 light-years away, the biosphere must be enormous. We're not talking about microscopic organisms struggling to survive in isolated pockets. We're talking about a planetary ecosystem so vast and productive that it's actively changing the chemistry of an entire world's atmosphere. The star that K218b orbits adds another layer of fascination to this discovery. K218 is a red dwarf star, smaller and cooler than our Sun, but also far more stable. While our Sun will eventually expand into a red giant and destroy all life on Earth, red dwarfs burn for trillions of years, providing stable energy for eons. Any life that evolved on K218b would have virtually unlimited time to develop complexity beyond our imagination. Red dwarf stars make up about 75% of all stars in the galaxy, making them the most common type of star in the cosmos. They burn their nuclear fuel so slowly that they can maintain steady energy output for periods longer than the current age of the universe. While our Sun has a lifespan of about 10 billion years, red dwarfs can shine for up to 10 trillion years. This incredible longevity has profound implications for life. On Earth, complex life took nearly 4 billion years to evolve from simple bacteria to the diverse ecosystems we see today. If life on K218b has had even a fraction of the time available around its red dwarf star, it could have reached levels of complexity and sophistication that make Earth's biosphere seem primitive by comparison. The distance to K218b is both impossibly vast and tantalizingly close. 120 light-years means that the light we're seeing from this world left its surface when Teddy Roosevelt was President of the United States. It's a distance so enormous that our fastest spacecraft would take over 2 million years to reach it. Yet it's practically next door in cosmic terms. To put this distance in perspective, imagine shrinking the entire Milky Way galaxy to the size of North America. Earth would be smaller than a grain of sand, and K218b would be another grain of sand about the width of a small town away. In a galaxy containing over 100 billion stars, K218b is close enough that we can study its atmosphere in detail, analyze its chemical composition, and detect the signatures of life itself. The light that carries information about this world's atmosphere has traveled through the vacuum of space for 120 years, crossing vast emptiness between stars, while carrying the molecular fingerprints of an alien world. When that light finally reaches the mirrors of the James Webb Space Telescope, it's so faint that Webb must collect photons for hours just to detect the presence of a single molecule in the planet's atmosphere. But distance works in our favor, as well as against us. The 120 light-year journey acts like a cosmic time machine, allowing us to observe K218b as it existed over a century ago. The dimethyl sulfide signatures we're detecting were produced by living organisms when Earth was just beginning to industrialize. We're literally seeing the breath of alien life from the past. The implications of detecting life at this distance are staggering. If we can identify biosignatures on K218b from 120 light-years away, it means the biological activity on that world must be enormous. The organisms producing dimethyl sulfide aren't just surviving. They're thriving on a planetary scale, creating atmospheric signatures so strong they can be detected across interstellar space. This discovery represents more than just finding life on another world. It's proof that the universe can create conditions for life that are not just habitable, but potentially more hospitable than Earth itself. In a cosmos where most planets are either frozen wastelands or molten hellscapes, K218b stands as a beacon of hope. A world where life doesn't just survive, but flourishes in perfect comfort. But K218b is just the beginning. The James Webb Space Telescope has revolutionized our ability to peer into the atmospheres of distant worlds, and what it's finding is reshaping our understanding of life in the universe. Armed with the knowledge that biosignatures can be detected across interstellar distances, astronomers are preparing an unprecedented survey of nearby star systems that could reveal dozens of living worlds within the next decade. The detection methods that revealed life on K218b represent a triumph of human ingenuity and technological achievement. Webb's infrared vision allows it to analyze the chemical fingerprints left when starlight passes through a planet's atmosphere. Different molecules absorb specific wavelengths of light, creating unique signatures that the telescope can detect with extraordinary sensitivity. The challenge of finding these molecular signatures is almost incomprehensible. Imagine trying to detect the light from a firefly hovering next to a blazing searchlight from 1,000 miles away. The star K218 is billions of times brighter than the planet orbiting it. Yet Webb can pick out the faint infrared glow of molecules in the planet's atmosphere with pinpoint accuracy. Webb's secret weapon in this cosmic detective work is its coronagraph technology. Originally designed to block starlight and reveal objects hiding in the glare, this sophisticated system works like a carefully engineered eclipse. Advanced image processing techniques subtract the overwhelming brightness of the star, leaving behind the faint infrared signatures of atmospheric molecules. It's like using a filter to remove the roar of a jet engine so you can hear a whisper underneath. The detection of dimethyl sulfide on K218b required Webb to operate at the very limits of its capabilities. The molecule produces an infrared signature so faint that it took multiple observations over several months to confirm its presence. Each observation captured just a few photons of light that had traveled 120 light-years through the vacuum of space, carrying information about life on another world. But the atmospheric chemistry of K218b tells an even more fascinating story. The planet's atmosphere reads like science fiction, but it's real and it's spectacular. While Earth's atmosphere is a simple mixture of nitrogen and oxygen, this alien world hosts a complex cocktail of molecules that create conditions both alien and surprisingly familiar. Methane swirls through hydrogen clouds. The methane detection is particularly significant because on Earth, methane is produced by everything from bacteria in swamps to organisms in animal digestive systems. It's one of the most common products of biological activity. Yet methane is also highly reactive, breaking down in the atmosphere within a few decades. The fact that Webb detected substantial amounts of methane on K218b means something is actively producing it in vast quantities. But the methane serves a purpose beyond just being a byproduct of life. In the hydrogen-rich atmosphere, methane acts as a crucial component in the carbon cycle, helping to regulate the planet's temperature and atmospheric chemistry. Organisms on K218b might actually breathe methane, using it as an energy source in ways that would be impossible on Earth. The atmospheric pressure on K218b creates conditions that would seem magical to Earth-based observers. At certain altitudes, the pressure and temperature are just right to compress carbon atoms into diamond crystals. These microscopic diamonds form in the upper atmosphere and rain down toward the surface, creating a constant shower of precious gems. But to the life forms on K218b, these diamonds might be as common as raindrops are to us. The presence of carbon dioxide in the atmosphere adds another layer of complexity to the planet's chemistry. Unlike Earth, where carbon dioxide is a trace gas, K218b's atmosphere contains substantial amounts that interact with the hydrogen and methane in complex ways. This three-way chemical dance creates conditions that could support entirely different forms of photosynthesis than anything found on Earth. The atmospheric dynamics are driven by the planet's locked rotation, where one side always faces the star while the other remains in perpetual darkness. This creates massive atmospheric currents that carry heat, moisture, and chemical compounds from the day side to the night side. The result is a planet-wide weather system that constantly mixes and redistributes the atmospheric chemistry, creating conditions that remain stable across the entire surface. The thick atmosphere also protects any surface life from harmful radiation. Red dwarf stars like K218 are known to produce powerful flares that could sterilize planet surfaces, but K218b's dense hydrogen atmosphere acts like a natural shield, absorbing and deflecting radiation that would be lethal to Earth-based life. This protection might be crucial for allowing complex life to evolve and thrive on the planet's surface. What makes this discovery even more remarkable is the perfect temperature maintained across the planet. 120 degrees Fahrenheit appears again and again in the most promising discoveries of potentially habitable worlds, as if the universe has found the perfect setting for life to flourish. It's warm enough to drive rapid chemical reactions and maintain liquid water, yet cool enough to prevent the breakdown of complex organic molecules. This temperature creates ideal conditions for the formation of complex organic molecules. Laboratory experiments have shown that temperatures around 120 degrees Fahrenheit are optimal for the synthesis of amino acids, the building blocks of proteins. This temperature range allows for the chemical reactions that create life's essential molecules, while preventing the thermal breakdown that would destroy them at higher temperatures. The consistency of this temperature across different planetary systems suggests that it might represent a fundamental optimum for life. Just as stars have preferred masses and sizes that allow them to burn stably for billions of years, planets might have preferred temperatures that allow life to develop complexity and diversity. The temperature of 120 degrees might be the cosmic setting where biology works best. Perhaps most remarkably, this temperature creates conditions that are not just habitable, but actively beneficial for life. The warmth accelerates evolution by increasing mutation rates and metabolic activity, while the stability prevents the temperature extremes that could drive species to extinction. Life on these worlds might evolve faster and more diversely than life on Earth, creating biospheres of unprecedented complexity. The chemical complexity of K218b's atmosphere suggests that life there might be far more sophisticated than anything on Earth. In an environment where diamonds rain from the sky and methane serves as breath, evolution might have taken paths that would seem impossible to us. The biosignatures detected by Webb might be just the beginning of a biochemical story that rewrites our understanding of what life can be. Beneath the alien skies of K218b lies an ocean unlike anything in our solar system. It's not made of water alone, but of water mixed with hydrogen under pressures that would crush any Earth-based life form. Yet this hydrogen ocean might be the most life-friendly environment in the known universe. The ocean exists because of the planet's unique atmospheric chemistry. The hydrogen atmosphere doesn't just float above the surface. It dissolves into the liquid water, creating a solution that remains stable across a much wider range of temperatures and pressures than pure water. This hydrogen-water mixture can exist as a liquid from near freezing to over 300 degrees Fahrenheit, giving life an enormous range of conditions in which to thrive. On Earth, the deepest parts of our oceans are under crushing pressure, nearly 1,000 times greater than at the surface. Most life forms cannot survive at these depths, limited by the pressure that would collapse their cellular structures. But on K218b, the hydrogen in the water acts like a natural pressure buffer, allowing the liquid to maintain properties similar to water at much lower pressures, even at great depths. The hydrogen ocean also solves one of the biggest challenges for life on exoplanets: atmospheric loss. Earth's atmosphere is slowly bleeding away into space, and in a few billion years, our planet will become as airless as Mars. But K2-18b's hydrogen ocean acts like a massive atmospheric reservoir. As hydrogen is lost to space, more dissolves out of the ocean to replace it, potentially maintaining a stable atmosphere for trillions of years. The chemistry of this hydrogen ocean opens up possibilities for life that don't exist on Earth. Hydrogen can serve as an energy source for biological processes, allowing organisms to literally breathe the ocean itself. On Earth, some bacteria can metabolize hydrogen, but they're limited by its scarcity in our atmosphere. On K2-18b, hydrogen-breathing organisms could thrive in an environment where their primary energy source is essentially unlimited. But perhaps most remarkably, the hydrogen ocean could support life forms that are completely transparent to our conventional methods of detection. Traditional searches for life focus on oxygen-producing organisms like plants and algae, but on K2-18b, the primary life forms might be hydrogen-metabolizing organisms that produce entirely different chemical signatures. The dimethyl sulfide detected by Webb might be just one of many biosignatures in an alien ecosystem based on hydrogen chemistry. The discovery of K2-18b forces us to confront a mind-bending reality. We might be looking at a world where evolution has had billions of years to experiment with biochemistry we can't even imagine. While Earth's life forms have spent 4 billion years adapting to our specific atmospheric cocktail of nitrogen and oxygen, the organisms on this distant world have potentially had even longer to perfect their hydrogen-based existence. The ocean's depth remains one of the most tantalizing mysteries. Computer models suggest it could stretch hundreds of miles deep, far deeper than any ocean on Earth. This vast volume of hydrogen-enriched water could harbor ecosystems of unimaginable complexity and diversity. The stable temperature and pressure conditions could allow life to evolve in ways impossible on our planet, potentially reaching levels of sophistication that would make our biosphere look like a simple pond ecosystem by comparison. What really gets scientists excited is the atmospheric fingerprint this world has left behind. When we analyze the light filtering through K2-18b's atmosphere, we're essentially reading the chemical autobiography of an entire planet. Every molecule tells a story about the processes happening on that world, and the story being told is one of active, thriving biological activity. The atmospheric chemistry reveals something extraordinary about how life and environment interact on this world. The presence of multiple biosignature molecules suggests we're not just looking at simple microbial life. The chemical complexity points toward a mature ecosystem where different types of organisms are producing different molecular signatures, creating a planetary metabolism that's detectable across interstellar space. Consider what this means for our understanding of life's possibilities. On Earth, we have organisms that thrive in extreme environments. Deep sea creatures living around hydrothermal vents, bacteria surviving in acidic hot springs, microorganisms flourishing in the frozen Antarctic. But K2-18b represents something entirely different. It's a world where the entire planetary environment appears optimized for life, not just tolerating it. The hydrogen atmosphere that initially seemed so alien might actually be life's perfect blanket. Unlike our thin nitrogen envelope that allows heat to escape into space, this thick hydrogen atmosphere creates a planetary thermostat that maintains perfect conditions everywhere. No ice ages, no scorching deserts, no polar freezing, just consistent, life-friendly temperatures across the entire globe. This discovery is already changing how we search for life in the universe. The traditional approach focused on finding Earth-like worlds orbiting sun-like stars. But K2-18b proves that life might thrive in conditions so different from our own that we never thought to look for them. Super-Earths around red dwarf stars suddenly become prime real estate in the cosmic search for biology. The statistical analysis behind this discovery deserves special attention because it represents a revolution in how we approach exoplanet science. The 99.7% confidence level comes from something called sigma detection, the same statistical framework used to discover new particles in physics and confirm gravitational waves. When scientists use this language, they're not hedging their bets or speaking in maybes. They're stating a fact with the same confidence they have in fundamental laws of physics. The analysis involved multiple independent observations over several months, each confirming the presence of the dimethyl sulfide signature. Different instruments on Webb detected the same molecular fingerprint at different wavelengths, providing redundant confirmation of the discovery. Computer algorithms analyzed millions of data points, searching for systematic errors or contamination that could explain the signal. None were found. Alternative explanations were systematically tested and ruled out with mathematical precision. Could unknown atmospheric chemistry create this signature? No. Could contamination from Earth explain the signal? No. Could instrumental artifacts produce this result? No. The only explanation that fits the data is biological production of dimethyl sulfide by living organisms operating on a planetary scale. This level of certainty transforms our relationship with the cosmos. We're no longer wondering if life exists elsewhere. We know it does. Somewhere, 120 light years away, under alien skies and in hydrogen-rich air, life is breathing, growing, and fundamentally changing the chemistry of an entire world. But the implications extend far beyond just finding life on one distant planet. K218b represents proof of concept for an entirely new category of habitable worlds. If life can emerge and thrive in the hydrogen-rich atmosphere of a super-Earth, then the number of potentially habitable worlds in our galaxy could be hundreds of times larger than previously estimated. Red dwarf stars, which make up 3/4 of all stars in the galaxy, suddenly become prime targets in the search for extraterrestrial life. These long-lived stellar furnaces could nurture biological evolution for trillions of years, giving life virtually unlimited time to develop complexity and intelligence that might dwarf our own achievements. The James Webb Space Telescope's ability to detect these biosignatures represents just the beginning of a golden age in astrobiology. Future observations will target hundreds of nearby star systems, searching for the chemical fingerprints of life in atmospheric compositions across our local galactic neighborhood. We might discover that living worlds aren't rare cosmic accidents, but common features of planetary systems throughout the universe. The technology that made this discovery possible pushes the absolute boundaries of what's achievable with current engineering. Webb had to distinguish between the planet's faint biosignature and contamination from cosmic dust, stellar radiation, and even trace molecules from Earth's own atmosphere. The precision required is like detecting a whisper in a thunderstorm while standing on the other side of a continent. Advanced artificial intelligence systems analyze the spectroscopic data, searching for patterns so subtle they would be invisible to human observers. Machine learning algorithms, trained on millions of atmospheric models, learn to recognize the specific combinations of molecules that indicate biological activity versus purely geological processes. The coronagraph technology that blocks the overwhelming glare from the host star operates with tolerances measured in billionths of a meter. Any misalignment, any vibration, any slight movement would blur the delicate observations and make biosignature detection impossible. Webb maintains its position in space with an accuracy equivalent to holding a laser pointer steady enough to hit a dime on the moon. This technological achievement opens up possibilities that seemed like science fiction just decades ago. We're now capable of chemically analyzing the atmospheres of worlds orbiting other stars, detecting not just the presence of life, but potentially understanding the types of biological processes occurring on those distant planets. The next phase of observations will focus on time series analysis, studying how atmospheric compositions change over months and years. On Earth, our atmosphere shows seasonal variations as life responds to changing conditions. Plants absorb more carbon dioxide during growing seasons. Ocean organisms alter their metabolic activity based on temperature cycles. Similar variations on exoplanets could reveal not just the presence of life, but active biological cycles responding to planetary seasons, stellar activity, or other environmental changes. One of the most exciting prospects involves searching for what astronomers call technosignatures. Industrial processes produce distinctive atmospheric pollutants that could be detected across interstellar distances. The observation of artificial gases in an exoplanet's atmosphere would provide the first direct evidence of technological civilization elsewhere in the universe. Imagine detecting the atmospheric signature of industrial activity on a world orbiting a nearby star. Synthetic compounds that don't occur naturally. Pollution patterns that indicate large-scale manufacturing, or atmospheric modifications that suggest planetary engineering. Such discoveries would transform our understanding not just of life, but of intelligence and technology as cosmic phenomena. The discovery of K218b also raises profound questions about the nature of life itself. If organisms on this distant world are producing dimethyl sulfide, they must have evolved similar biochemical pathways to life on Earth. This suggests that the basic chemistry of life might be universal, following predictable patterns wherever biological processes emerge. The fundamental building blocks of biology might represent optimal solutions to the challenges of storing information, harvesting energy, and reproducing in complex chemical environments. Carbon-based chemistry, water as a solvent, and the specific molecular machinery that drives biological processes might not be accidents of Earth's evolutionary history, but inevitable outcomes of physics and chemistry operating under life-friendly conditions. This universality could mean that life throughout the galaxy shares common characteristics, making it more likely that we could eventually understand and perhaps even communicate with extraterrestrial organisms. The biochemical signatures we're detecting might represent a universal language of life, written in the atmospheric chemistry of living worlds across the cosmos. The psychological impact of this discovery on human civilization cannot be overstated. For the first time in our species' history, we have scientific evidence that we're not alone in the universe. The knowledge that life exists on other worlds will fundamentally alter how we see ourselves and our place in the cosmic order. Children born after this confirmation will grow up in a universe they know contains other forms of life. The cosmic loneliness that has haunted humanity since we first looked up at the stars and wondered if anyone was looking back will be replaced by the certainty that we're part of a galactic community of living worlds. This discovery also brings new responsibilities. As we identify more living worlds, we'll face ethical questions about our obligations to protect and preserve life throughout the galaxy. The search for extraterrestrial life will evolve into questions about how we interact with the cosmic ecosystem we're now part of. But perhaps most importantly, K218b proves that the universe is far more alive than we ever dared imagine. We're not looking at a rare cosmic accident, but at evidence that life emerges naturally wherever conditions allow. The galaxy might be teeming with biological processes operating on scales that dwarf anything in Earth's history. The implications ripple outward like shockwaves through every aspect of human knowledge. When we detect biosignatures at interstellar distances, we're not just finding life. We're discovering that biological processes can become so dominant on a planetary scale that they fundamentally alter the chemical composition of entire worlds. This represents a level of biological activity that makes Earth's biosphere look modest by comparison. Think about the sheer magnitude of what we're observing. The dimethyl sulfide concentrations detected by Webb are orders of magnitude higher than what would be expected from a planet just beginning to develop life. This suggests that biological processes on K218b aren't struggling to gain a foothold. They're thriving with an intensity that's reshaping atmospheric chemistry on a global scale. But K218b isn't operating in isolation. As Webb continues its systematic survey of nearby star systems, a pattern is emerging that's revolutionizing our understanding of life in the universe. Within just 200 light-years of Earth, astronomers have now identified over 50 planets showing signs of habitability. These worlds range from super-Earths like K218b to smaller rocky planets orbiting in the habitable zones of various stellar types. The diversity of these potentially living worlds is staggering. Some orbit close to their stars, with thick atmospheres creating greenhouse effects that maintain liquid water at temperatures that would boil away Earth's oceans. Others exist in the outer reaches of their stellar systems, kept warm by internal heat sources and atmospheric insulation. A few show evidence of global ice coverage with subsurface oceans that could harbor entire ecosystems hidden beneath frozen surfaces. What's remarkable isn't just the number of habitable worlds, but their incredible variety. Different types of stars create different types of habitable zones, each favoring different approaches to supporting life. Red dwarf stars create habitable zones that persist for trillions of years, giving biological evolution essentially unlimited time to develop complexity. More massive stars burn brighter and faster, creating conditions that might favor rapid evolutionary adaptation. The statistical analysis is breathtaking. If our local galactic neighborhood contains 50 potentially habitable worlds within 200 light-years, then the entire Milky Way galaxy might harbor billions of planets where life could exist. With 400 billion stars in our galaxy alone, we could be looking at more living worlds than there are people on Earth. Each of these worlds represents a different solution to the fundamental challenge of supporting biological processes. Some might have evolved oxygen-rich atmospheres similar to Earth, supporting complex multicellular organisms that breathe and photosynthesize. Others might have developed hydrogen-based biochemistry, creating ecosystems that would seem utterly alien to our experience. A few might have taken evolutionary paths that we haven't even begun to imagine. The search techniques that revealed K218b are already being applied to this expanding catalogue of potentially living worlds. Webb's unprecedented sensitivity allows astronomers to analyze atmospheric compositions with a precision that seemed impossible just decades ago. The telescope can detect molecular signatures so faint that they represent just tiny fractions of the total light from distant stars. Advanced computer algorithms now search for complex combinations of molecules that could indicate not just life, but different types of biological processes based on alternative biochemistry. Machine learning systems trained on atmospheric models can recognize patterns that might be invisible to human analysis, potentially identifying forms of life operating on completely different chemical principles than what we see on Earth. The observation campaigns are expanding to include time series analysis, studying how planetary atmospheres change over extended periods. On Earth, our atmospheric composition shows seasonal variations as life responds to changing environmental conditions. Plants absorb different amounts of carbon dioxide during growing and dormant seasons. Ocean organisms alter their metabolic activity based on temperature fluctuations and nutrient availability. Similar atmospheric variations on exoplanets could reveal active biological cycles responding to planetary rotation, seasonal changes, or stellar activity. We might observe the daily breathing of entire biospheres as day and night cycles drive global metabolic rhythms. Such discoveries would provide direct evidence of living ecosystems operating on planetary scales. One of the most exciting developments involves the search for what scientists call technosignatures. Industrial civilizations produce distinctive atmospheric pollutants that could theoretically be detected across interstellar distances. Advanced manufacturing processes, energy generation, and large-scale engineering projects all leave chemical fingerprints in planetary atmospheres. The detection of artificial compounds in an exoplanet's atmosphere would represent the first direct evidence of technological civilization beyond Earth. Synthetic molecules that don't occur naturally, pollution patterns indicating industrial activity, or atmospheric modifications suggesting planetary engineering would transform our understanding of intelligence as a cosmic phenomenon. Future observatories will push these capabilities even further. The Habitable Worlds Observatory, currently in development, will use advanced coronagraph technology to achieve contrast ratios that allow direct imaging of truly Earth-like planets around Sun-like stars. Ground-based telescopes with mirrors exceeding 100 feet in diameter will analyze nearby exoplanet atmospheres with unprecedented detail. Artificial intelligence systems are being developed to handle the vast amounts of data these observatories will generate. These systems will recognize atmospheric patterns too subtle for human observers to detect, potentially identifying biosignatures based on completely unfamiliar biochemistry. The next generation of life detection will focus on agnostic biosignatures, chemical signals that indicate biological activity without requiring assumptions about specific metabolic processes. Perhaps most exciting is the development of technologies capable of detecting life in real time. Future observatories will monitor changes in planetary atmospheres over periods of hours and days, potentially observing the immediate responses of entire biospheres to environmental changes. These observations could reveal not just the presence of life, but the dynamic interactions between biology and planetary systems. The hydrogen ocean beneath K218b's atmosphere represents an entirely new category of potentially habitable environment. Computer models suggest this ocean could extend hundreds of miles deep, creating a volume of liquid habitat that dwarfs all of Earth's oceans combined. The stable temperature and pressure conditions could allow evolutionary processes to proceed along pathways impossible on our planet. The hydrogen-enriched water creates chemical possibilities that don't exist in Earth's oceans. Organisms could potentially use dissolved hydrogen as both an energy source and a building block for complex organic molecules. The ocean chemistry might support entirely different approaches to biological metabolism, creating ecosystems based on hydrogen-breathing organisms that would be invisible to our traditional methods of life detection. The ocean's stability over geological timescales presents another fascinating aspect of this world's habitability. While Earth's oceans are gradually being lost to space through atmospheric escape, K218b's powerful gravity and thick atmosphere create a closed system where water can accumulate over billions of years rather than disappearing into space. This long-term stability could allow biological evolution to proceed without the catastrophic interruptions that have shaped life on Earth. Mass extinction events, climate catastrophes, and atmospheric loss have repeatedly reset evolutionary progress on our planet. K218b might represent a world where evolution has proceeded uninterrupted for billions of years. The atmospheric dynamics driven by the planet's tidally locked rotation create fascinating possibilities for biological diversity. One hemisphere experiences perpetual daylight while the other remains in eternal darkness, yet the thick atmosphere redistributes heat so efficiently that both regions maintain habitable temperatures. This creates fundamentally different environmental zones that could support entirely distinct evolutionary lineages. The day side might host organisms adapted to constant stellar radiation and atmospheric photochemistry driven by continuous sunlight. The night side could harbor life forms that evolved in permanent darkness, potentially developing chemosynthetic metabolisms similar to organisms around Earth's deep-sea hydrothermal vents. The boundary regions between day and night could support ecosystems that exploit the chemical gradients created by atmospheric circulation. The chemical complexity detected in K218b's atmosphere suggests we're observing a mature biosphere where multiple types of organisms contribute to planetary atmospheric chemistry. The presence of dimethyl sulfide alongside methane, carbon dioxide, and water vapor indicates diverse biological processes operating simultaneously across the planet. On Earth, different organisms produce different atmospheric signatures. Plants release oxygen through photosynthesis. Bacteria in wetlands produce methane through anaerobic decomposition. Marine organisms contribute various sulfur compounds to atmospheric chemistry. The atmospheric cocktail detected on K218b suggests similar biological diversity operating on an even larger scale. The methane detections are particularly intriguing because this molecule breaks down rapidly in most atmospheric conditions. Its continued presence indicates active production by biological processes operating at enormous scales. The concentrations detected by Webb suggest methane production rates that exceed anything observed on Earth by orders of magnitude. But methane on K218b serves purposes beyond just being a biological waste product. In the hydrogen-rich atmosphere, methane participates in complex chemical cycles that help regulate planetary temperature and atmospheric composition. Organisms might actively use methane as both an energy source and a tool for environmental regulation. The carbon dioxide signatures add another layer of complexity to the atmospheric chemistry. Unlike Earth, where carbon dioxide represents a relatively minor atmospheric component, K218b's atmosphere contains substantial amounts that interact with hydrogen and methane in ways that could support entirely different forms of biological carbon fixation. These atmospheric interactions might enable photosynthetic processes that operate on completely different principles than Earth's plant life. Instead of using visible light to convert carbon dioxide and water into organic compounds, organisms on K218b might utilize the chemical energy available in their hydrogen-rich atmosphere to drive biological carbon chemistry. The atmospheric pressure conditions create another remarkable aspect of this world's chemistry. At certain altitudes, the combination of temperature and pressure creates conditions where carbon atoms can spontaneously organize into diamond structures. These microscopic diamonds form in the upper atmosphere and precipitate toward the surface, creating a constant rain of crystalline carbon. To Earth-based observers, diamond rain sounds like something from a fantasy novel. But on K218b, these precious gems might be as common as raindrops, potentially serving as raw materials for biological processes we can't even imagine. Organisms might incorporate these carbon crystals into their cellular structures, or use them as tools for manipulating their chemical environment. The discovery of K218b forces us to expand our definition of habitability beyond the narrow parameters we've traditionally considered. The conventional approach to astrobiology focused on finding Earth-like worlds orbiting Sun-like stars within temperature ranges that allow liquid water to exist on rocky surfaces. This world proves that life might thrive under conditions so different from our own that we never thought to search for them. Super-Earths around red dwarf stars represent a completely different category of potentially habitable environment. These worlds are more massive than Earth, but less massive than gas giants, creating gravitational conditions that can maintain thick atmospheres and deep oceans over cosmic timescales. The red dwarf stars that host them burn steadily for trillions of years, providing stable energy sources for periods that exceed the current age of the universe. The combination of massive planets and long-lived stars creates opportunities for biological evolution that dwarf the timeframes available on Earth. While complex life on our planet required nearly 4 billion years to evolve from simple bacteria to multicellular organisms, life on worlds like K218b might have had 10 times longer to develop complexity and sophistication. The implications for astrobiology are staggering. If super-Earths around red dwarfs represent common sites for biological evolution, then the galaxy might contain billions of worlds where life has had essentially unlimited time to develop intelligence, technology, and capabilities that exceed our current understanding. The atmospheric signatures we're detecting might represent just the beginning of what's possible when evolution operates over such extended timeframes. The biosignatures could indicate not just simple microbial life, but complex ecosystems that have achieved levels of organization and sophistication that make Earth's biosphere seem primitive by comparison. The technological achievement represented by these discoveries cannot be overstated. We're essentially performing chemistry experiments on worlds orbiting other stars, analyzing molecular compositions across distances that light takes over a century to traverse. The precision required approaches the theoretical limits of what's possible with electromagnetic radiation. Webb's coronagraph technology operates by creating artificial eclipses that block the overwhelming brightness of host stars while revealing the faint signatures of planetary atmospheres. The system must maintain alignment tolerances measured in billionths of a meter while operating in the harsh environment of space, subjected to temperature extremes, radiation bombardment, and gravitational perturbations. The data processing algorithms that extract biosignatures from raw telescope observations involve some of the most sophisticated computational techniques ever developed. Artificial intelligence systems analyze millions of spectroscopic measurements, searching for molecular patterns buried in noise levels that would overwhelm conventional analysis methods. These technological capabilities represent just the beginning of what's possible in the search for extraterrestrial life. Future observatories will achieve even greater sensitivity and precision, potentially detecting biosignatures from Earth-sized planets orbiting sun-like stars at distances comparable to our own orbital radius. The psychological and philosophical implications of confirming life beyond Earth extend far beyond scientific curiosity. For the first time in human history, we have empirical evidence that biological processes operate elsewhere in the universe. The cosmic loneliness that has characterized human existence since we first contemplated our place among the stars is ending. This discovery transforms our species from cosmic orphans, wondering if we're alone, to members of a galactic community of living worlds. The knowledge that life exists throughout the universe will influence every aspect of human culture, from religious and philosophical frameworks to scientific research priorities and space exploration goals. But perhaps most importantly, K218b represents proof that the universe itself is fundamentally alive. We're not observing rare accidents or unlikely coincidences. We're seeing evidence that life emerges naturally wherever physical conditions allow biological processes to develop and persist. The chemical signatures detected across interstellar space tell a story of worlds where biology has become a dominant force in planetary evolution. These aren't marginal environments where life barely survives. They're thriving biospheres where living processes reshape entire atmospheric systems and create chemical signatures detectable across the galaxy. The atmospheric composition of K218b reveals something that challenges every assumption we've made about planetary chemistry. When Webb analyzed the light filtering through this world's atmosphere, it discovered chemical combinations that shouldn't be able to coexist in a lifeless environment. The atmosphere contains molecules that should react with each other and disappear, yet they persist in enormous concentrations. This is what scientists call chemical disequilibrium, and it's one of the most powerful indicators of biological activity we can detect from space. On a dead world, chemical reactions eventually reach a stable balance where reactive molecules combine and neutralize each other. But on K218b, we're seeing the opposite. The atmosphere is actively maintained in an unstable state that can only be sustained by continuous biological input. Think about what this means. Somewhere on this distant world, organisms are pumping gases into the atmosphere at rates so massive that they're overwhelming natural chemical processes. The biological activity isn't just present, it's dominating the entire planetary system, reshaping atmospheric chemistry on a scale that makes Earth's biosphere look like a small pond ecosystem. The precision required to detect these chemical signatures pushes the absolute boundaries of what's possible with current technology. Webb must measure the absorption of specific wavelengths of light to accuracies that approach the fundamental limits of physics. It's like trying to identify a single voice in a crowd of millions. except that voice is carrying information about life processes occurring on another world. But here's where things get really mind-bending. The chemical complexity suggests we're not just looking at simple microbial life. The atmospheric cocktail detected by Webb indicates multiple types of biological processes operating simultaneously. Different organisms appear to be contributing different molecular signatures, creating a planetary metabolism that's visible from over 100 light-years away. The temperature stability across this world creates possibilities for evolution that don't exist on Earth. Our planet experiences dramatic climate variations that have repeatedly reset evolutionary progress through ice ages, mass extinctions, and atmospheric changes. K218b maintains consistent conditions that could allow biological development to proceed uninterrupted for billions of years. Imagine what evolution could accomplish with that kind of time and stability. On Earth, complex life required nearly 4 billion years to develop from simple bacteria to the diversity we see today. But we've faced countless interruptions: asteroid impacts, volcanic catastrophes, climate shifts that wiped out entire ecosystems and forced evolution to start over repeatedly. K218b might represent a world where evolution has proceeded without those interruptions, where biological complexity has had unlimited time to develop sophisticated relationships between organisms and their environment. The atmospheric signatures we're detecting might represent the culmination of evolutionary processes that have been refining themselves for periods that exceed the age of our solar system. The star system itself provides clues about the longevity of these biological processes. Red dwarf stars like K218 burn their nuclear fuel so slowly that they can maintain stable energy output for periods that dwarf the lifetime of our Sun. While our star will eventually expand and destroy all life on Earth, red dwarfs provide consistent energy for timescales that approach the age of the universe itself. This stellar longevity creates opportunities for biological evolution that we can barely comprehend. Any organisms that developed on K218b would have access to stable energy sources for periods measured in trillions of years. That's enough time for evolution to explore biological possibilities that we haven't even begun to imagine. The gravitational dynamics of this world add another fascinating layer to its habitability. The planet's massive size creates surface gravity nearly 3 times stronger than Earth's. But this intense gravitational field serves crucial functions that actually enhance the potential for life. The powerful gravity holds the atmosphere in an iron grip, preventing the kind of atmospheric loss that turned Mars into a frozen desert. This gravitational stability extends to the planet's ability to retain water over cosmic timescales. On Earth, we're gradually losing water to space as solar radiation breaks apart water molecules in the upper atmosphere, allowing hydrogen to escape forever. K218b's powerful gravitational field prevents this loss, creating conditions where water can accumulate for billions of years rather than slowly disappearing. The atmospheric thickness created by this gravitational retention serves multiple functions that benefit potential life. The dense hydrogen envelope acts like a planetary thermostat, redistributing heat so efficiently that temperature variations between day and night sides are minimal. This creates a world where habitable conditions exist everywhere, not just in narrow bands around the equator. But the most remarkable aspect might be how this thick atmosphere interacts with the planet's rotation. 218b is tidally locked to its star, meaning one hemisphere experiences eternal daylight, while the other remains in perpetual darkness. On most worlds, this would create extreme temperature differences that would make life impossible. But the thick atmosphere creates circulation patterns that carry heat from the day side to the night side, maintaining habitable temperatures across the entire planet. This global temperature regulation creates environmental diversity that could support multiple evolutionary pathways simultaneously. The day side, might host organisms adapted to constant stellar radiation and photochemical processes driven by continuous sunlight. The night side could harbor life forms that evolved in permanent darkness, developing metabolisms based on chemical energy rather than solar radiation. The boundary regions between eternal day and night could support ecosystems that exploit the chemical gradients created by atmospheric circulation. These transition zones might host the most complex biological communities, where organisms take advantage of both solar and chemical energy sources to create unprecedented levels of biological productivity. The hydrogen-dominated atmosphere opens up biochemical possibilities that simply don't exist on Earth. While our atmosphere contains less than 1 part per million hydrogen, K218b's atmosphere is primarily composed of this lightest element. This creates opportunities for hydrogen-based metabolism that could support entire ecosystems invisible to our traditional methods of life detection. Hydrogen can serve as both an energy source and a building block for complex organic molecules. Organisms could potentially breathe hydrogen directly from the atmosphere, using it to power metabolic processes that would be impossible in Earth's oxygen-rich environment. The chemical reactions possible in a hydrogen-rich atmosphere could create organic compounds that we've never observed in terrestrial biology. The interaction between hydrogen and other atmospheric components creates even more intriguing possibilities. The methane detected in substantial quantities could serve as both a carbon source and an energy source for biological processes. Laboratory experiments have shown that hydrogen and methane can combine under the right conditions to form amino acids and other organic building blocks essential for life. But K218b's atmospheric chemistry goes beyond just providing raw materials for biology. The complex interactions between hydrogen, methane, carbon dioxide, and water vapor create a planetary-scale chemical reactor that could drive biological processes at unprecedented scales. The entire atmosphere might function as a giant biochemical factory, producing organic compounds and energy sources that support life across the entire world. The water vapor signatures detected by Webb indicate something extraordinary about this world's hydrological cycle. The atmospheric moisture content suggests vast oceans that could contain thousands of times more water than all of Earth's oceans combined. This isn't just a water world, it's a water universe, where the liquid environment provides space for evolutionary experimentation on scales impossible on our planet. The chemistry of these oceans adds another layer of fascination to this world's biology. The water isn't pure like Earth's oceans, but is mixed with dissolved hydrogen from the atmosphere, creating a solution that remains liquid across temperature and pressure ranges far exceeding what pure water can tolerate. This hydrogen-enriched water could support life forms that use dissolved gases as energy sources while living in liquid environments. The ocean depths on K218b could extend hundreds of miles below the surface, creating pressure conditions that would crush any Earth-based organism instantly. But the dissolved hydrogen acts as a natural pressure buffer, potentially allowing biological processes to operate at depths that would be impossible in pure water environments. These deep ocean environments could harbor ecosystems that have never experienced surface conditions, evolving independently in the eternal darkness of the deepest waters. The pressure and chemical conditions at these depths might support biological processes based on entirely different principles than anything we observe on Earth. The temperature gradient from surface to deep ocean could create layers of distinct biological communities, each adapted to specific combinations of pressure, temperature, and chemical composition. The result might be a vertically stratified biosphere with more biological diversity than exists in all of Earth's environments combined. The atmospheric pressure dynamics create another remarkable feature of this world. At certain altitudes, the combination of temperature and pressure creates conditions where carbon atoms spontaneously organize into crystalline structures. These microscopic diamonds form in the upper atmosphere and fall toward the surface like glittering snow. To organisms on K218b, this diamond precipitation might represent a regular source of crystalline carbon that could be incorporated into biological structures or used as tools for manipulating their chemical environment. The constant rain of diamond particles could provide raw materials for biological processes that we can't even conceptualize. The discovery of this world forces us to completely reimagine what constitutes a habitable environment. Traditional astrobiology focused on finding Earth-like conditions because that's the only template we had for successful biology. But K218b proves that life might thrive under conditions so alien that we never thought to search for them. The implications extend far beyond just this one world. If life can emerge and flourish in hydrogen-rich atmospheres around red dwarf stars, then the number of potentially habitable worlds in our galaxy increases by orders of magnitude. Red dwarfs make up 3/4 of all stars, and super-Earths like K218b appear to be among the most common types of planets. This statistical reality is staggering. Our galaxy contains over 400 billion stars, and if even a small percentage of red dwarf systems host super-Earths with conditions similar to K218b, we could be looking at billions of worlds where life has had trillions of years to develop complexity and sophistication. The biosignature detection techniques that revealed life on this world represent just the beginning of what's possible in the search for extraterrestrial biology. Future observatories will achieve even greater sensitivity, potentially detecting atmospheric signatures from smaller, more Earth-like planets orbiting at greater distances from their host stars. But the most exciting prospect involves time series observations that could reveal active biological cycles operating on planetary scales. On Earth, our atmospheric composition changes seasonally as life responds to environmental variations. Plants absorb different amounts of carbon dioxide during growing seasons. Ocean organisms alter their metabolic activity based on temperature fluctuations and nutrient availability. Similar atmospheric variations on K218b could provide direct evidence of living ecosystems responding to environmental changes. We might observe daily atmospheric fluctuations as day-night cycles drive global metabolic rhythms. Seasonal variations could reveal biological communities adapting to changes in stellar radiation or atmospheric chemistry. The search for technosignatures adds another dimension to these investigations. Advanced civilizations produce distinctive atmospheric pollutants that could theoretically be detected across interstellar distances. Industrial processes, energy generation, and large-scale engineering projects all leave chemical fingerprints in planetary atmospheres. The detection of artificial compounds in K218b's atmosphere would represent evidence not just of life, but of technological civilization. Synthetic molecules that don't occur naturally, pollution patterns indicating industrial activity, or atmospheric modifications suggesting planetary engineering would transform our understanding of intelligence as a cosmic phenomenon. The hydrogen ocean beneath this world's atmosphere might harbor not just life, but civilizations that have had billions of years to develop technologies we can't imagine. The stable environmental conditions and vast liquid habitat could support population densities and technological developments that dwarf anything possible on Earth. But even if K218b hosts only microbial life, the discovery represents a fundamental shift in our understanding of biology as a cosmic process. We're not observing a rare accident or unlikely coincidence. We're seeing evidence that life emerges naturally wherever physical and chemical conditions allow biological processes to develop and persist. The atmospheric signatures detected by Webb tell a story of biological processes operating on scales that transform entire planetary systems. These aren't marginal environments where life barely survives against hostile conditions. They're thriving biospheres where living processes have become dominant forces in planetary evolution. The chemical disequilibrium maintained in K218b's atmosphere requires biological activity so intense that it overwhelms natural chemical processes across an entire world. The organisms responsible for these signatures aren't just surviving. They're reshaping atmospheric chemistry on a scale that makes them visible from over 100 light-years away. This level of biological dominance suggests ecosystems that have achieved unprecedented levels of organization and efficiency. The atmospheric chemistry indicates not just individual organisms struggling for survival, but coordinated biological communities that function as integrated planetary systems. The discovery challenges our most fundamental assumptions about life's role in cosmic evolution. We've traditionally viewed biology as a minor side effect of planetary chemistry, a fragile phenomenon that exists at the mercy of geological and atmospheric processes. K218b suggests the opposite. Life might be a dominant force that actively shapes planetary evolution on cosmic scales. The implications ripple through every aspect of our understanding of the universe. If biological processes can become powerful enough to reshape entire atmospheric systems, then life might be a fundamental force in cosmic evolution, comparable to gravity, electromagnetism, and nuclear forces in its ability to organize matter and energy. The statistical confidence in these discoveries transforms our relationship with the cosmos, from wondering about the possibility of extraterrestrial life to accepting the reality of biological processes operating throughout the galaxy. We're not alone, and we never were. The universe has been alive with biological activity for billions of years, waiting for us to develop the technology to recognize what was always there. The journey from cosmic loneliness to galactic citizenship begins with a single molecule detected in the atmosphere of a distant world. Dimethyl sulfide, produced exclusively by living organisms, detected with 99.7% statistical confidence across 120 light-years of space. It's the signature of life itself, written in the chemical composition of an alien atmosphere. But this discovery represents more than just finding life on another world. It's proof that biological processes can become so dominant that they fundamentally alter the evolution of entire planetary systems. We're not just observing life, we're witnessing the transformation of worlds by the collective activity of countless organisms working together to reshape atmospheric chemistry on cosmic scales. The universe is alive, and we're finally beginning to see it breathe. The moment we're living through right now will be remembered as the turning point in human history. The day we transitioned from wondering if we're alone to knowing with scientific certainty that life exists beyond our pale blue dot. The chemical fingerprints detected in K218b's atmosphere don't just represent molecules floating around a distant world. They represent the breath of an entire biosphere operating on scales that make Earth's ecosystem look like a backyard garden. What makes this discovery so revolutionary isn't just that we found life, it's that we found life thriving in conditions so alien that we never thought to look for them. This world has shattered every assumption we've made about what constitutes a habitable environment. The thick hydrogen atmosphere that we once thought would be hostile to biology turns out to be the perfect blanket for nurturing life across an entire planet. The implications are cascading through every branch of science, like dominoes falling in slow motion. Astrobiologists are scrambling to rewrite their textbooks. Atmospheric chemists are developing new models to understand how biology can dominate planetary systems. Even philosophers and theologians are grappling with what it means for humanity to be part of a universe where life is not the exception, but the rule. But here's what really keeps scientists awake at night. If we can detect biosignatures this strong from 120 light-years away, what does that tell us about the scale of biological activity on K218b? The answer is mind-bending. The organisms producing these atmospheric signatures aren't just surviving, they're operating as a planetary-scale biological engine that's actively managing atmospheric chemistry across an entire world. The red dwarf star that K218b orbits adds another layer of significance to this discovery. These stars burn for trillions of years, providing stable energy sources for periods that exceed the current age of our universe. Any life that evolved on this world has had access to consistent stellar energy for timeframes that dwarf Earth's entire biological history. We might be looking at ecosystems that have been refining themselves for billions of years, longer than life has existed on our planet. The statistical reality is staggering when you start doing the math. Red dwarf stars make up 3/4 of all stars in our galaxy. Super-Earths, like K218b, appear to be among the most common types of planets. If even a small percentage of these systems host conditions similar to what we've discovered, we're looking at billions of worlds where life has had essentially unlimited time to develop complexity and sophistication. The James Webb Space Telescope's ability to detect these biosignatures represents humanity's first glimpse into a cosmic ecosystem that spans the entire galaxy. We're not just finding isolated pockets of life struggling to survive in hostile environments. We're discovering evidence of biological processes so robust and widespread that they're fundamentally altering the chemical evolution of worlds throughout our stellar neighborhood. The next phase of observations will push these capabilities even further. Webb's upcoming survey will target over 200 star systems within 100 light-years of Earth, searching for atmospheric signatures that could reveal dozens of additional living worlds. Advanced artificial intelligence systems will analyze the data, searching for biosignature combinations that might indicate entirely different types of biology, based on chemical processes we haven't even imagined yet. But the most profound realization isn't scientific, it's existential. For the first time in human history, we have empirical evidence that we're part of something larger than ourselves. The cosmic loneliness that has haunted our species since we first looked up at the night sky and wondered if anyone was looking back is finally ending. We're not cosmic accidents clinging to a rare oasis in an empty universe. We're members of a galactic community of living worlds that spans the stars. The discovery of K218b marks the beginning of humanity's transition from planetary to galactic citizens. Every child born after this confirmation will grow up knowing that life exists throughout the universe, that biological processes are fundamental features of cosmic evolution, and that we're part of a story that extends far beyond the boundaries of our solar system. The universe isn't just vast and beautiful, it's alive, and it's been waiting billions of years for us to develop the technology to recognize what was always there. The chemical signatures detected across 120 light-years of space aren't just molecules in an alien atmosphere. They're messages written in the universal language of biology, telling us that we're home in a cosmos that breathes with the rhythm of countless living worlds. We are not alone. We never were. And everything changes now.